overarching theme that allows us to think about materials chemistry, then there's a rather beautiful set of ideas introduced in parallel by Ashwin's group and also by Andre Bernavig's group at Princeton that nowadays goes under the name of topological quantum chemistry. So that asks, essentially, it sort of blends these ideas of thinking about symmetry and topology with the understanding of Wannier states and so on that come in from DFT. And it really allows you to do materials discovery with topological ideas to the fore. And I sort of encourage you to look at that. And similarly, there are other types of things like nodal line semimetals that I won't talk about. But in the end, all these things are ultimately, the reason they're interesting is because there's lots of materials that come in. And I'm going to talk about sort of initial materials. So in some sense, the first candidates for a lot of these things, or in some cases, rather good experimental candidates that we can study. But of course, if you want a comprehensive survey of materials and experiments, well, that's a moving target because new ideas, new materials come online all the time. And so this is just to say that I'm going to give you a very highly personalized view of the field. And I'd say that, it's really important if you find these ideas interesting to look at other sources. So there's a rather excellent review article by Ashwin, Peter Armitage, and Jean Millet on generally Weil and Dirac semimetals and solids that sort of has a comprehensive literature review of all the work that's been done. And that dates back a couple of years. And I think they worked hard enough to give enough of an overview that even though it's about 3 years old, it still has the bulk of the things that you'll need. They sort of presaged all the modern developments in many ways in that review. And some of the transport signatures I'm going to talk about are in another very nice review, a little older, by my collaborator Pavan Hozur and Jialiang Qi at Stanford. And so they wrote a very nice review article on how to search for topological semimetals using their unconventional transport signatures. So I should have probably flipped this around. This review article is probably relevant to what I'll say today, and this one is more relevant to what I'll say tomorrow, and we'll extend some of those ideas further. Okay, so this is just to sort of set the groundwork for what I want to talk about and narrow the scope of the discussion. So just to give a historical overview, and some of these things may have been touched upon in the lectures that you've already seen in this series, I think if you look back, topology over the past 40 years now has been playing an increasingly important role in understanding materials, in particular quantum materials. So the earliest instance of topology in sort of a material science setting, as opposed to a statistical physics setting. So topology has played a role in statistical physics for thinking of things like Kosterlitz-Thouless transitions and magnets and superfluids and things like that. But in terms of material science, the first time topology played a serious role in some sense is the discovery of the quantum Hall effect in the 1980s. And I want to flag that this was discovered because of materials advances that allowed people to build two-dimensional heterostructures of gallium arsenide and silicon and so on, and look for field effect transistors. So this beautiful piece of fundamental physics came out of very prosaic applied questions of trying to build field effect transistors in these, in these semiconductor devices. And so the quantum Hall effect famously is the coexistence of a robustly quantized Hall conductivity with the absence of longitudinal conductivity at certain magic densities as set by the magnetic field. This was in some sense the main example of topology in the solid state. There was also the fractional quantum Hall effect, which is the quantum Hall effect with the role of interactions. But the next big advance came in 2007, following on work by Charlie Kane and Eugene Millet in predicting a notion of a robust quantum spin Hall effect. And following and Andre Bernavig, Shucheng Zhang and collaborators predicted that this would be a place to look for these would be in mercury telluride quantum wells developed by Lawrence Molenkamp's group in Würzburg. And very shortly thereafter, people realized that the idea of topology didn't have to be limited to two-dimensional materials or two-dimensional quantum wells or heterostructures, but instead one could actually locate these in 3D systems. And in particular, you could have a 3D analog of the quantum spin Hall effect. And that started off the sort of modern topological revolution. For instance, people started looking at topological superconductivity and sort of engineering 1D analogs of topological superconductors. And you might have seen that there's a lot of controversial and exciting developments in thinking about Majorana zero modes in these hybrid semiconductor-superconductor devices. And much more recently, people have argued that you can actually see the original sort of simplest example of a topological insulator, which is the Chern insulator. I'll talk a little bit about this. Where you have gap protected edge states and all the signatures of the integer quantized Hall effect, but without an external magnetic field. So what unifies all these examples is that in all these cases, these are all, I call these quantum Hall effect, but I could have just crossed out effect and put in the word insulator. And all of these are insulators. In all these cases, you have an insulator, which are made special by the fact that the filled bands have some topological property that distinguishes the vacuum of the insulator, where nothing is happening because it's an insulator, but nothing is happening in a different way than nothing happening in the outside vacuum. And because of that, the boundary between the insulator and the outside has some kind of special surface states. And partly the reason one can think about these in a robust, mathematically sensible way is because you're gapped in the bulk, and you're gapped, our vacuum is gapped in the sense that there are no excitations unless I pay the creation energy of an electron in the outside world. And so because of that, we can sharply define an interface between these two gapped regions. So about let's say 10 years ago, people started asking whether you could make sharp statements topologically to phases that lack a bulk gap. Are there cases you can talk about where we're thinking about somehow the fact that the bulk isn't insulating, but instead has some interesting physics going on its own? So it's some kind of internal, it's either metal or a semi-metal as opposed to being a semiconductor or an insulator. And can topological aspects of that gapless bulk still somehow make it special and lead to interesting physics? And so what I'll focus on today is, in some sense, the simplest example of a gapless bulk, which is a semi-metal. And this is one of those things where different people mean different things by semi-metal. So generically, if you open a Ashcroft and Mermin, you'll see that a semi-metal is defined as a solid whose conductions and valence bands just overlap or touch in energy. So if I plot the energy and then plot a density of states, so this is states or DOS, you see that in a metal, your chemical potential just lies somewhere in the middle of some filled state, so you have a robust Fermi surface. And in an insulator, you have a large gap. So your filled states and empty states have a big energy gap. Now, a semiconductor has a smaller energy gap, but from the point of view of topology, a semiconductor and an insulator are basically the same thing. Now, when people talk about semiconductors, they sort of start making distinctions between N-type and P-type semiconductors because of the fact that there's either acceptor or donor energy levels near the band. But from the point of view of topology, all these states are effectively insulating because there's a bulk gap. What happens if you start off in an insulator, what you can do is bring these things together to where they just touch. Now, where they just touch, what I'm drawing here is a density of states. But if you think about insulating bands, suppose you started off with an insulator with an indirect band gap, and you start bringing the energy bands together, you'll have electron and hole pockets. And I'm going to restrict to the case of what I'll call perfect compensation. And what this means is that there's no Fermi volume, even though I have conducting degrees of freedom in the bulk. What I mean by no Fermi volume is if I add up the electron Fermi surface and add up the whole Fermi surface, so the area enclosed by those, the total density of electrons and the total density of holes in the system exactly cancel, so there's no net density. So if you think about that a little bit, there are various possibilities. Your Fermi surface can consist of isolated points, or it can have a single point like this, where electron and hole bands just touch at some single point. You could have two sets of such points. You could have many such points. You could have lines along which bands touch, which typically will require more symmetry. You can have equal volume pockets of electrons and holes. So this is imagining where you have, you could imagine a band structure that looks like this with the chemical potential, something like that, if I sketched it. Or you could have, much more complicated band structures. But if I integrate the area enclosed by the hole pockets and integrate the area enclosed by the electron pockets, the total volumes will match up. So in the end, there is no net density in the system. So that's what I mean by semi-metal, to set up the rules of the game. Right? So is that definition clear? Is anything unclear at that point? I'd probably pause a little bit because I'm going to move into the sort of set out the plan of the lecture. So this is sort of disclaimers to say exactly what I'm focusing on in these lectures. So I don't see any questions, so maybe I should keep going.
We don't see any questions, so yeah, I think
Great. Just want to pause because it's always a little harder.
Absolutely, yeah.
Okay, so just to step back, I want to try and build the theory of topological semimetals by remembering that there's two different ways one can think about topological arguments in materials, and they both play a role in insulating states. So roughly speaking, I'll call them the Thouless approach and the Laughlin approach after the people who were most associated with these ideas, although lots of other people have built those ideas in and used them in clever ways. So the Thouless approach is what's most familiar to many people because it says what you care about. If you like, the Thouless approach of thinking about solids is saying the following. So if I open up my Ashcroft and Mermin, there's large chapters of band theory. And they spend a lot of time drawing, what people sometimes call spaghetti diagrams, where you have, these horrible pictures of band structures across the Brillouin zone, and they tell you about how the energy disperses in the Brillouin zone. So if you like, those diagrams focus on one aspect of the Schrodinger equation. They focus on the energy levels of the Schrodinger equation. But we know that the Schrodinger equation also spits out energy bands it spits out wave functions. So if you like, the Thouless approach says take the properties of those wave functions seriously, and in particular, rather than look at local details of the wave functions, you ask some sort of subtle questions about how those wave functions, these block functions that you get by solving the Schrodinger equation in a periodic potential, how those block functions wind as you move across the Brillouin zone. And so this is the topology of energy bands is saying something about how the wave functions behave as you move across the Brillouin zone. And in some sense, this can be mapped onto classic questions in topology because it's asking about certain properties of functions from the Brillouin zone, which is a torus, to some more complicated space, which is the set of occupied bands and how those sort of functions behave. And if you ask about the topological classification of those functions with various technical details to do with worrying about whether the addition of a trivial set of isolated atomic sites would change the answer. It turns out that's a well-posed problem in the mathematical field of topology. It goes under the fancy name of K-theory if you want to do it carefully. But ultimately, what we're asking is some statement about the topology of how energy bands, when I talk about energy bands, I mean the energy wave functions, wind as you go across the Brillouin zone. And indeed, if you take that and then ask, well, there's also some symmetries that these things must obey, such as time reversal symmetry, inversion symmetry, parity symmetry, charge conjugation symmetry in the original sort of setting, but also you could ask about various crystal symmetries. Then you get a very rich table of all the different topological ways, different distinct classes of band structures that you can get. And this is how you get the periodic table of topological insulators. And so basically what this says is this is the topology of single electron states, because what we're talking about is solving the single electron Schrodinger equation in the presence of all the ions in the crystal. That's not a many body problem. That's a free particle problem effectively. Now in DFT, when you're doing this in a DFT setting, you've incorporated some of the interactions, in fact, in writing down pseudopotentials and so on. But in the end, the wave functions you get are obtained by solving some effective single particle problem. So in that sense, we're still talking about individualized electron wave functions and how they wind and thinking about the physics of those wave functions. Maybe a little less known, and I'll spend only a very little bit of time on it, but just to be complete and tell you that both aspects have a role to play, is what I'll call the Laughlin approach. And what the Laughlin approach does is say, rather than think about individualized electronic wave functions and how they wind, it asks about how the entire many-body ground state evolves under some kind of adiabatic transformation. And what this lets you do is make some non-trivial statements about what kind of many-body ground states are acceptable in these complicated systems. And this actually leads to much more exotic phenomena, such as ground state degeneracies and fractionalization. So if you like, the Thouless approach is the root of the integer quantum Hall effect, and the Laughlin approach is the root of the fractional quantum Hall effect. And roughly speaking, the two aspects of topology in solid state are looking for topological single particle physics and topological many particle physics, and that's where these two approaches come in. So roughly speaking, if you want to phrase it in the language of insulators, the Thouless approach is how we think about the topology of band insulators, and the Laughlin approach is how to think about the topology of interacting insulators, what are traditionally known as Mott insulators. And what I want to argue today, and this is what I'll spend most of today focusing on, is how to apply these two approaches to thinking about semi-metallic systems. Okay, so here's a plan for the lectures today and tomorrow. So what I'll do today is give you an overview of how to think about band theory and topology starting, and there are many ways to introduce the subject. Some are very formal mathematically, some are very intuitive physically. I'm going to try and take a middle ground where I want to pick the universal physics. For me, I want to pick a route to do this, which allows you to think in terms of, it allows you to translate some formal theoretical ideas into thinking about things like transport, which we actually measure and experiment. So I want to focus in this language on very phase physics, because for me, once you understand that, a lot of the other generalizations become more straightforward. And so I want to focus on the ideas of band theory and topology and identify the conditions under which topological semimetals appear and explain what makes topological semimetals topological. So what I'll do is talk about Berry's phase in solids and give you the best known example of topological semimetals, which are Weil and Dirac semimetals, and give you some experimental settings they come in, talk a little bit about their properties. And then maybe in the very last bit, I'll spend some time talking about a different class of semimetals, which I'll call filling and forced semimetals. This is a distinct set of semimetals which allows us to think about different types of topological semimetals and where their physics comes in. And so it turns out these have, in some sense, an intimate relation with crystal symmetry in a way that maybe Weil and Dirac semimetals have a distinct relationship with crystal symmetry. Then tomorrow, what I'll do is take these ideas, and as I said, I'm introducing this from the perspective of Berry phases because I believe that's the easiest way to look at the manifestations of non-trivial topology in the Weil and Dirac case, and give you a list of experiments, a very personalized list because it's sort of experimental probes that I've been involved with predicting that are sensitive to these topological effects. And in particular, I'll focus very briefly on signatures in zero magnetic field, and I'll try and convince you that really what one should do is look at physics in finite magnetic field, where one can look at the particularly special lambda level structure of Weil and Dirac semimetals and use that to understand physics related to what is known as the chiral or Adler-Bell-Jekyll anomaly. And I'll argue that clever multi-terminal transport measurements can actually really shed a lot of light into the underlying topological band structures. And then again, as I'll do today, I'll spend a brief period of time talking about how this idea of filling and forced semimetals allows us to look for interesting new correlated states of matter in crystals. Okay, and so this is what I'm going to do today. That's the plan. And so let me start off with talking about Berry phase in solids. Okay. So again, I'll pause one more time and ask if there's any uncertainty in what I propose to cover, or if there are things that people think I should add on to this, because it's sort of built to be a little bit flexible, so I can switch to the Blackboard and address any questions if there are any. Looks like there aren't any or no questions in the chat either, so let me go ahead. So, if I step back and say, what does band theory link? What is the role of band theory in solids? At a very basic level, what band theory does is link transport properties of systems with symmetry. If you like, this is the great accomplishment of Bloch's theorem, and in some sense, it's a really great accomplishment of the quantum theory and quantum theory of solids, because essentially the ingredients that go into band theory are Bloch's theorem, which is a statement about discrete translational symmetry and how to think about eigenstates of the Schrödinger equation in the presence of the discrete translational symmetry. And in this language, we form energy bands. We say that rather than have a continuum of states that go over all allowed momenta, the momenta fit into a Brillouin zone. And so what you get is energy values of the energy with where there are no allowed states, and values of the energy where there are allowed states. And combining this with the Pauli exclusion principle that tells us that you can only fill in, only one electron in of each spin at each momentum state, what you find is that this allows us to draw a sharp line between metals and insulators. So if you like, this was the first real explanation of why some things are insulating and why some things are metallic. So we understand now that metals form when you have partially filled bands or gapless systems, and insulators form when you have fully filled bands, and therefore there's an energy gap to create an excitation. So if you like, until then, the idea, and what I want to emphasize is until then, understanding why something was insulating was always a little bit of a puzzle, because if I think of some more generic model of an atom, you might worry, understanding why metals and insulators depend on the way things are precisely arranged in a crystal is a subtle point, because For instance, this tells you, if you start from a chemistry perspective, you can say, oh, if things were tightly bound, then they should always be insulating. But we know that that's not true. When you put things together in a crystal, the electrons can become released from their individual atomic sites and move over the crystal. And so thinking about the sort of Bloch's theorem gives us the freedom to think in sort of, as a physicist as opposed to a chemist, think in terms of symmetry grounds on why some things are why metals are metals and insulators are insulators. Right, and there are sort of wrinkles on top of this. As I pointed out, in semimetals, the filled bands can touch other bands in energy, and in semiconductors are just insulators with a very narrow gap. So we know that band theory tells us how to connect transport with symmetry. I want to also tell you that this is only half the story. So if I think about the energy bands as just real numbers, the energies that I'm associating, E of k, the dispersion that I get, then it's a statement about band theory linking transport with symmetry. But it turns out band theory also contains information that links transport with topology, and I want to motivate that. And the best way I know how to motivate that is to think about the easiest way to incorporate energy bands and solids into transport theory. So this is semi-classical electron transport in solids. It's actually a rather beautiful section in Ashcroft and Mermin. It's sort of several, I think more than one chapter discusses this. It goes back to Felix Bloch and Rudolf Peierls in the 1930s, and also Jones and Zener. So the basic idea is the following. We know that in free space, we know how to incorporate electric and magnetic fields with the electrons. We know what to do. Once you put on Schrodinger equations in the crystal, what you get is Bloch bands. So you have some Bloch Hamiltonian and you have some Schrodinger equation states. And so you get a set of energy bands, which I've written over here, where En of k has some, and what I'm drawing E0 here is just saying that this is the energy in the absence of any external field. So H0 is the energy without any electric and magnetic field switched on. I get a set of Bloch bands. So what the semi-classical theory of electron dynamics does is say, let us try and recreate an electron out of the Bloch bands. So if you want to create a point-like electronic object in free space, what you do is create a wave packet. And that's when you give a particle-like interpretation. So let's do semi-classics, but instead of taking a wave packet of e to the I k dot r states, you take a wave packet of Bloch electrons. So you have a non-trivial Bloch wave function for these electrons. And so the reason we want to do this is when we work semi-classically, as long as we're not trying to resolve, as long as we obey the uncertainty principle and allow delta x, delta k to be greater than h bar over 2, then you can actually give a position and an average position and an average momentum to a wave packet, so we can treat it almost like a classical object. And what the semi-classical theory of transport in solids does is say, ask how wave packets evolve when electric and when E and B are switched on, when electric and magnetic fields are switched on. And so the key modification, if you open your Ashcroft and Mermin, it tells you the key modification is that the velocity is replaced by the group velocity of these wave packets, and that group velocity is given by the dispersion of the energy band. And so rather than have a standard velocity, what I have is dE dk in the solid, where E is now the energy bands. You can see that if I just started out with free particle dispersion p squared over 2m, this just gives me the familiar fact that the velocity is just p over m. But I'm doing something a little bit more rich because I'm now I'm allowing it to have additional features. For instance, this kind of incorporating this kind of detail allows me to distinguish between electrons and holes in solids. The second piece is that the force experienced by the electron, so the rate of change of the wave packet's momentum, is just given by the Lorentz force. And this is where the external electric and magnetic fields go in. So you have a Lorentz deflection and you have electric field force. And if you incorporate these details, you can get remarkably successful. You can explain the properties of solids with great success. So for instance, you can explain electron conductivity and hole conductivity in solids. You can understand where the effective mass approximation comes from. You can even describe quantum oscillations, the sort of semi-classical limit of Landau levels, and talk about Shrubnikov-de Haas and de Haas-Van Alphen and explain why they allow you to extract properties of the Fermi surface in this language. It's a very, very successful theory. And in some sense, it's the go-to theory to thinking about transport because it sort of focuses in on the essential details of the band structure. So this is why I like this approach. But now I want to step back and look at this approach as a theorist thinking about symmetry. So I look at this equation over here and say, this, if I take this h bar and put it over here, this starts to look a lot like, and let me be a theorist and say h bar and E are 1. Let me call this dE dk an electric field in K space. Then I get an equation that looks, I'm just relabeling things. I get something look like x dot is minus E twiddle in this language. So this looks very, very similar to the equation I got for K dot, but it looks asymmetric, right? Because I have an equation which has a magnetic field over here, and I don't have an analog B tilde over here. What am I looking for in that language? Well, I'd like to have an equation that looks like there's a K dot, a rate of change of K, multiplying some effective pseudomagnetic field in K space. And this is just motivated by saying I have some equations that look very similar. Wouldn't it be nice if those equations had some nice duality, that they were very similar, like position and momentum were interchangeable? That would be very, very pretty. And somehow this equation without this term looks less pretty. I mean, maybe that, but then I start thinking, maybe there is such a term, but I happen to look only at examples where this term was non-zero. So I start thinking, where could such a term come in? Well, that term comes in because I have a quantity K that's associated with a wave packet. And I know that that quantity K is, if I go back to where that K came from, that was a parameter of my effective Hamiltonian that I solved to get these wave functions. So the evolution of that parameter is something to do with how my block Hamiltonian evolves as I move through the Brillouin zone. And so if I think about what a wave packet is doing, the fact that I could build a wave packet only out of states within some set of bands or some single band in this simple example, I'm reminded of some old aspect of quantum mechanics where I was trying to go, I'm staying in an energy band. Roughly speaking, that means that I'm staying in, I'm following some eigenstate of a Hamiltonian around. And in some sense, I know where this idea of following an eigenstate is familiar to me from my elementary quantum mechanics class. And it sounds a lot like this idea of Berry phase. So I want to try and make that idea of Berry's phase more concrete. And I would be remiss in not mentioning that the classical analog of this for optics, of course, was discovered by Pancharatnam. So many people refer to it as the Pancharatnam-Berry's phase. I only refer to it as Berry phase because it's a bit of a mouthful and also because I'm focusing on it in the quantum context. So let's just go back and review Berry's phases for a second, just so that everybody's on the same page and we've set terminology. So the basic idea of Berry's phase is to consider the adiabatic evolution of a Hamiltonian that depends on some set of parameters. Generically, this R is a vector. I'm not going to draw vector symbols on top, but it could be some large number of parameters that themselves are evolving in time. So I think of some Hamiltonian that's labeled by some parameters that evolves in time. And I'm making the assumption that the evolution, how R varies in time, is done adiabatically slowly so that the system is always in an instantaneous eigenstate. And so if I think about some system, let's say I'm in the ground, for simplicity, you could take the ground state, but you could take any eigenstate. So say I'm in the 10th state above the ground state. What I'm imagining is that that number, the 10th eigenstate, is always in the 10th eigenstate. I'm never going to go into the 9th eigenstate or jump into the 11th eigenstate. So for instance, here I'm in the 3rd eigenstate as a function of energy. And as I adiabatically evolve, I'm always going to stay in that 3rd eigenstate. I'm never going to leave that state. I'm not, and I'm going to instantaneously stay in that limit. And you can sort of see that this is, if I think of this, instead of adiabatic evolution, I replace it with K. This is precisely what it means to remain in an energy band as you evolve, except that K is somehow, my wave packet is moving, its K values change, its center of mass momentum is changing in time, and I'm insisting that it changes in such a way that the system remains in, the electronic wave function remains in a single band as we go. Okay? And so the way Berry phase is usually motivated is saying, well, I know how the eigenstate ought to evolve because after all, I have some n of r. I need to pick up some phase unitarily as I evolve, but otherwise I'll just imagine that I'm always staying in the instantaneous eigenstate. So what I mean by n of r of 0 is saying, so if I pick some set of values of r that specifies a Hamiltonian, and n of r of 0 is just the nth eigenstate of that Hamiltonian. So I say, if I start off in the nth eigenstate of the Hamiltonian at time t equals 0, I'll end up at the nth eigenstate of the Hamiltonian at time t, maybe with some phase. And we'll go, and this is what is referred to as the dynamical phase. In fact, this is too fast. There's a missing piece, which is Berry's phase. And so let's see where those two pieces come from. So first of all, I wrote this piece, this time integral of e to the I en of t prime dt prime. And the reason I do that is instantaneously between time t and t plus dt, you'll pick up an, if I think of time evolution, for an instant of time between time t and t plus dt, I can imagine that I evolved with the Hamiltonian h of, basically I can imagine I evolved with h of t. Well, if I evolve with h of t, let me just write this down. I can imagine I evolved with at time t, h of t. I have the Hamiltonian h of t, and I have n of t. So I know that if I evolve one candidate for n of t plus delta t, if I ignore the fact that the Hamiltonian has changed, this is just e to the I en of t delta t, where en of t is the energy eigenvalue at time t of state n. And in principle, this energy eigenvalue could be a function of time, because if you look at this evolution I drew over here, you see that as time evolves, that energy moves around. And so I have to diagonalize the problem at each instant of time and move. So that's perfectly fine. I know about how that works. And I just add up that for each bit of time. That's how I got this thing, and that's sensible for adiabatic evolution. I don't need to worry about mixing into other states because I made the assertion at the beginning that I'm always going to stay in the nth eigenstate. So the only thing that can happen is a phase of this kind. But the subtlety, though, is that n of t plus delta t is not the same as n of t. So what I tried to write down was that this is n of t, but this is not so innocuous because the actual wave function itself has changed. So Berry's phase is really how you account for the fact that the wave function at time t plus delta t and the wave function at time t could be a little bit different. And so I won't go into this. It's I think my favorite place to read about this is Shankar's textbook, Principles of Quantum Mechanics, is a very careful discussion of Berry's phase. But after some work, you can show that you pick up an extra phase that has to do with the instantaneous change in the wave function. So you can check that this n of r gradient n of r is saying, it's essentially measuring, if you like, this quantity is roughly speaking n of r of t plus delta t, n of r minus n of r, n of r. Of course, this quantity is just 1. So basically, that's what this is measuring. And if you expand this in gradients and solve the problem, you can see that symbolically what you should get is a derivative of this form, right? So that's basically what I'm trying to do in this calculation. So you can see that if you properly normalize everything, you'll get the infinitesimal change is like delta t n of r grad r n of r. There's an infinitesimal phase that you pick up, and basically exponentiating that gives you a Berry phase like this. So that's a sketch of how that calculation works, but I think that many of you will be familiar with it, so I don't want to belabor the point. So, you might say, why do I care about a phase? Because normally we're taught that the overall phase of a wave function is unimportant. Quantum mechanics can't measure overall phases. And in fact, if you formally look at the definition of quantum mechanics, a state is associated, not a quantum state is a ray in Hilbert space. It has this ambiguity that I can pick whatever global phase I want and it doesn't matter. And that's true because normally what I could just do is say, if all that's changing, if I'm staying in this adiabatic state and the only thing that can change as I evolve is that my kets are getting redefined at each point, then I can always remove it. More generally, if I have a large number of filled states, I could argue that what I have to do is do some unitary transformation among the filled states, and I can always remove the generalization of Berry phase to that example. But in some cases, the evolution of the system is periodic. So for instance, suppose I had some complicated parameter space. And so this is what I'm drawing is some trajectory in R, in the space of R, drawn two-dimensionally here, but you can think of this as a million dimensions, it doesn't really matter. So my Hamiltonian is evolving, but R at t, at some t final is the same as R of 0. So I've gone through a loop in parameter space. Then imagine that I have the Berry phase for a cycle. So I calculate the Berry phase over this entire cycle, and I get a non-zero answer. Then I cannot simply redefine things along the trajectory and remove that Berry phase, because there isn't an ambiguity in the integral of something over a closed loop. An integral with open boundary conditions, you say, I don't really care, but once I have a closed loop, one has to be very careful. And that's where there's a non-trivial aspect of Berry phase. And so there's a way that makes this a bit clearer is to think of Berry phase in terms of a vector potential. So if I think of this object, I n grad n, then let me call that quantity curly a sub n. So it's some vector potential. Then the phase I wrote down is just the integral of that vector potential over some contour. And we know that usually vector potentials don't matter. You can get rid of them. And in fact, there's a very concrete statement of how this gauge transforms, because you can see that if n of r, if I take the state n of r and go to e to the I theta of r, let me actually be a little bit more precise. Change this, chi of r, n of r, then you can convince yourself that a n of r goes to a n of r plus grad chi, which is really how a vector potential does, the correct transformation law for a vector potential. So that's quite nice, because I see that this is behaving exactly how a vector potential will do, and the phase redefinition of the wave function at each point is precisely the transformation law for a vector potential under a gauge transformation. So everything is holding up. And so we know that if you have a vector potential, the physically meaningful quantity is the magnetic field and not the vector potential. And so the reason for that is just Stokes' theorem. If I have the integral over a closed loop of a dot r, then I can just convert that in an integral over the surface of the loop of the flux of that vector potential, of the flux of the effect of the magnetic field through that loop. And so the Berry phase accumulated along a closed loop is just the Berry flux through the enclosed area of that loop. So this idea of Berry fluxes is very important, because what I'm going to do now is argue that this is important in understanding how energy bands behave in momentum space. So to see why this is important, remember that we're doing semi-classical dynamics. And so in semi-classical dynamics of block states, as opposed to electrons in free space, block states their momentum is restricted to live on a torus in momentum space. Classically, we say in units where the lattice spacing is 1, we identify k and k plus 2 pi. So the Brillouin zone is a torus. So that means that if you think about any semi-classical wave packet evolving in the Brillouin zone, its evolution has to be periodic. It has to complete a closed loop because it has to re-enter the Brillouin zone. So if you think about k evolving as the wave packet moves under the influence of x, so what I'm doing is semi-classics, and the reason the k is evolving is because I imposed external electric and magnetic field. So that, remember, k dot is controlled by external E and external B. So k dot is going to be non-zero. It's going to evolve in space because forces act on the particle. But as k evolves, it's forcing the wave packet, and therefore it's forcing the parameters, the Hamiltonian, and therefore of the block wave functions, to evolve in this Brillouin zone. But k itself is a periodic variable. So if I view this problem as adiabatic evolution in this classic way, which is what I'm doing when I think about wave packet dynamics, then I've got to get a non-trivial Berry phase. I have to worry about there being a non-trivial Berry phase. So in this language, k is playing the role of r of t, and it's a let me think of a two-dimensional Brillouin zone in general. So for my toy example, so then there's a wave vector k. I can take a gradient of k over here, and I can write down a curl. I mean, this works in other dimensions, but this is particularly nice in 2D. I can define a vector potential b of k as the curl, a Berry flux b of k as the curl of this vector potential. This object in here is my an of k that I defined. And if you actually put that into the semi-classical dynamics, you find exactly a kind of Lorentz force on the particle coordinate. And this additional contribution shifts the velocity. It says the velocity depends on the force on the rate of change of the wave packet, the center of momentum of the wave packet via this Berry phase. And this additional contribution was known as an anomalous velocity. And in fact, Karplus and Luttinger pointed this out in 1954, that these kinds of contributions come in. And in some sense, the modern theory of semi-classical transport in solids was really crystallized by Niu and Sundaram, who did this calculation very, very nicely and carefully. And Haldane then pointed out that it's sort of a universal feature allows us to think about properties of the Fermi surface in a very nice way. So there's sort of the long history to this problem over 50 years. So just to give you an example of where this can play a role, a rather famous example is that there's the conventional Hall effect, in which charge carriers are deflected due to an external magnetic field, and thus generates an additional voltage transverse to the current. And we know there's an important probe. It gives you the sign of the charge carriers and so on. And this can be understood from the semi-classical perspective without any Berry phase terms. But there's an intrinsic version of this anomalous Hall effect. Suppose I turn my magnetic fields to 0. So then there's this term is set to 0. This term can nevertheless give a non-trivial value. And it's important to note that to get this term to be non-zero, in some sense, you need there to be a time reversal breaking somewhere in the problem for it to integrate out to give you a non-zero value. But if you do that, what you find is that if there's some microscopic time reversal breaking due to magnetism or something else, or some currents that form in the system, but no external magnetic field, then the Berry phase of energy bands can give you an anomalous Hall contribution. And the way that's computed is, remember the quantized Hall conductance is defined in some 2D plane of the system. So the quantized Hall conductance measured in the XY plane is obtained by taking the Z component of the Berry of this Berry vector, Berry flux, and summing it over filled bands. So there's a Berry flux for each band, and there's an occupation of the band. And if you sum this quantity up over all the occupied bands in the system, so this is a Fermi function that tells you whether the band is occupied or not at that given temperature, that gives you a non-trivial anomalous Hall effect. Now, here's the special feature. Since it cares about the occupation of the bands, if you go to 0 temperature and your chemical potential lies in a gap, then this has a very simple form. It's the Fermi function, so it's 1 for all filled bands and 0 for all empty bands. And so if the Fermi energy lies in a gap way in an insulator, you pick up this integral is f of k is k for all states within the band. So this integral is just an integral. I can drop this term. So let me manipulate this a little bit. I can essentially take this term out, and this integral is over the Brillouin zone, but this sum is sum only filled bands. Okay. Now, when I take this integral, I pick up the total Berry flux from each filled band. Now it turns out that the integral of this Berry flux over the entire two-dimensional surface actually has to be 2 pi times an integer. That's a property, and that quantity is called this integer is known as the Chern number. So this might be familiar to some of you. And in some sense, this Chern number is also what makes the integer quantum Hall effect in a magnetic field a non-trivial topological phase, except that there is no Brillouin zone. What you do is use the magnetic Brillouin zone because you put on a magnetic field to do the same calculation. But in the end, what you end up with is that there's a quantized Hall conductance. It's E squared over H times an integer, and this integer is fixed as long as the Fermi energy is in the gap. But in this picture, I didn't put on an external magnetic field, and there's no Landau level story. So you get an integer quantum Hall effect without Landau levels. And in some sense, this is one of the reasons why Haldane won the Nobel Prize a couple of years, 3 years ago, was for identifying this scenario where you can get an integer quantum Hall effect without Landau levels. And in some sense, thinking about this more generally, asking about other topological quantities you can extract, even when the Berry phase itself is not so easy to look at, is how you get helical edge states and strong topological insulators, and their generalizations to 3D came out of thinking about these semi-classical pictures. So if you like, the semi-classical understanding of Berry phase is sort of the parent state for topological phases. It's really the sort of basic understanding came out of these semi-classical pictures that you can look at. So just to close this sort of introductory section, the reason we care about topological insulators and all their related systems is that they're fundamentally new phases of matter. And these topological properties are very universal. They're robust to disorder, they're robust to sample imperfections in many cases. And because of that, it may be possible to use them to engineer topologically protected quantum operations. But more generally, they're just exotic materials with potential for applications that we can't foresee. So for instance, if you think about the transition over the last 70 years, in 1947, in Bell Labs, this is the original transistor, and this is a scale model of a P. So the original transistor was the size of a P. And a P seems pretty small, but if you put a billion Ps together, they look pretty big, right? That's a large object. And this is why the original computers, even with transistors, would have been very big. I mean, they were much better than vacuum tubes, which are about the size of a potato. So it was a lot, putting a billion transistors, even of this size together, is a lot better than putting a billion vacuum tubes together, because they're much better. But in fact, the key idea is that you could miniaturize them so that in 2013, you can put 1.4 billion transistors onto the best Intel chip, and in the sort of 7 years since then, it's improved even further. But if you look at where this progress came in, you focus basically on miniaturization and clever design. How do you pack more things on a chip? How do you do fabrication, do very large scale integration? But what has not changed is that fundamentally what you're doing in all these transistors is still essentially switching the flow of charge around. You're not using any other degrees of freedom, you're still manipulating charge. But we know that there's other aspects of semiconductor devices. Electrons carry spin, they carry things like Valley quantum numbers, they carry a lot of other quantum numbers in semiconductor materials. And we've not really made much progress in coming up with ways to manipulate them. And that's basically because they're very hard to access. And so what topological materials might do is allow us to use charge properties to convert charge responses into Valley degrees of freedom or spin degrees of freedom, and then read in and read out. But once they're in terms of once you've injected information into charge and Valley, maybe the way we control the flow of that could be done in more creative ways. So it represents a different way of controlling the flow of light and charge, light and heat at the nanoscale, because you can use topological response functions to interconvert between charge and other degrees of freedom. So in sort of a more prosaic level, just forgetting about quantum computing, just from the point of view using quantum mechanics to manipulate charge transport, they offer new ways to do that. So the topological insulators that I talked about are things that are gapped in the bulk. And if you like, they're sort of the picture of the sort of invisible man. There's nothing going on in the bulk. There's the only thing that's interesting is everything that's around the bulk of the system. That's where you get these Dirac cones, non-trivial transport, all these things. What we have here is something a little bit more rich. There's something going on in the bulk. And the question is, can topology play a role even when the bulk is gapless? So I think I should pause here because it's about the perfect time to break, because what I'm going to do now with that introduction of how Berry phase plays a role is use that to go ahead and apply it to understanding one example of a topological phase, which is a topological vial semimetal. So let me pause there, and I think this is a good place to take a little bit of a break, settle down, and see if there are questions in the sort of background material.
Yeah, thanks, Sid. Any questions?
And I'm happy to answer any very basic questions because there's a lot of material. So these are sort of the basic ideas. So it's good to just get them straight with everyone.
I think if you you can also raise your hand and be happy to unmute.
Somebody raised
it. Yes, let's see. Right, I'll unmute you. Okay, you should be able to unmute yourself now.
They're not muted, they can unmute. They have to do it. Yeah.
Okay.
Yeah.
So the question is, when you say that the bulk is insulating and the surface states are metallic or conducting, is it in the EK sense, or is it actually physically, if I take a piece of bismuth selenide, which is a topological insulator, and actually there is surface states are metallic? I mean, is it in the band structure sense that you have the insulating and the metallic states, or actually in the physical real space also that is the case?
I see your point. You're asking basically the fact is that whether your bands could do, let me just go to the blackboard that I have. You're saying the bands could do something like this. This is an insulator from the point of view of mathematics, but from the point of view of actual transport or something like that, it may not be an insulator because there are, there's a picture like this. Is that the question you're asking, I guess?
Yes, that's yes.
Yeah. So I would say that, so that's a question of detail that has to do with some particular properties of chemistry. I would argue that topological classification can't rule this out. From the point of view of topology, you're allowed to, deform this. You're basically allowed to deform your chemical potential like that, basically because momentum is a good quantum number. So when I talk about the adiabatic transport, you see that I think a way to see it in terms of adiabatic transport is I could have stayed within this band and there's never an ambiguity because K is a good quantum number. So as K evolves, at each K I have a band gap. So from the point of view of mathematics, that's all I really need. But I agree with you that it's not entirely satisfactory. So from a prosaic point of view, what I'm doing is laying out the sort of idealized theoretical picture. Now, bismuth selenide does have this problem that there are lots of other things. I'm making many idealizations. I'm saying, let's take the cleanest sample so I don't have to worry about any doping into the system. I'm assuming I can tune the chemical potential into the gap in the idealized sense so that the thing is perfect stoichiometry where it's an insulator. Even in that, with those idealizations, I could end up in a situation like this. And it's very hard for me, you can't rule this out. So this is where the actual energy dispersion matters, because you see E of K is important. What you do in topological arguments is usually you say, well, E of K you can flatten this band and look at it essentially non-dispersing. And the only thing that gives you the ability to do that is basically the statement that, well, as long as there's a band gap, this can be done by just locally changing details of the Hamiltonian. I don't need to introduce long-range hoppings or anything like that. And that's usually the argument that, then you're classifying things where essentially the dispersion doesn't matter as a mathematical perspective. But of course, in any realistic system, you do care about the dispersion, and that is important. So maybe that's an answer that lays out the rules I'm following. I didn't answer your question in the sense that it's a very good one. And if you're actually looking at a material, you have to address whether it looks like this or whether it looks more like this idealized picture of having bands that look like that, where you have a happy band gap in the bulk. But from the topological point of view, these things are identical.
Yes, but I think the first slide, your first slide of this talk, I mean, there is some design of an experiment where we could really delineate the difference. I mean, access the wild states or Dirac states and all these things.
Yeah.
And the point is, any measurement actually would have some contribution from the surface state, some contribution from the bulk state, other than R-pace, which is purely surface states. And R-pace just tells you that those are states. But transport means there has to be a current that would flow in the surface states or something like that.
Yeah.
So in transport signatures, I mean, somehow probably I've made the next talk, I would request you to just cover what would be the real experimental manifestation. I mean, we agree there would be surface states, but current flowing in the surface states is different than just saying that there are surface states.
There are experimental. So I think I wasn't sure which you were talking about. So I'm talking about systems that are, there's a question even here, right? What I'm trying to say is the following. There's two things. This has a trivial bulk, whereas Weyl semimetal has some kind of Dirac points in the bulk. So the bulk is also interesting in a Weyl semimetal. But I would say that in the Weyl semimetal, the bulk is guaranteed to be gapless. You can't play the game of saying, oh, there's a limit in which just search for a new material, right? I have to confront the gapless case in the Weyl case. And we spend a lot of time thinking about sharp signatures in magnetic field. And we have several that allows you to pick out things that are flowing on the surface, things that are linked to the bulk anomaly. And we can, there is a bulk boundary correspondence where the surface states exist because of the bulk anomaly. But we can actually, I'll lay out tomorrow's lectures, I'll lay out specifically signatures that allow you to pick out what's non-trivial about the bulk that makes it different from a trivial bulk, and what's non-trivial about the surface, independent of what's going on in the bulk, that picks it out. And you can use that to really look at current transport there. Yeah.
Okay, thank you.
So today I'm just laying the groundwork for what goes on, and then tomorrow I'll focus on the details. Yeah. Other questions? Just quickly. Okay, in that case, should I go ahead, Niladri?
Yeah, I don't see any other questions in the chat. So if you'd like to start, yeah.
Okay. Great. So what I want to do now is focus on the simplest example of a topological semimetal, which is a vial semimetal. And in fact, while a lot of excitement on these materials came in very recently, they've actually been known from the work of Conyers Herring in his PhD thesis in the 1930s, way back in the 1930s. So what is a vial semimetal? So basically, a vial semimetal happens when a pair of bands, and I'll underline the two, touch at a single point. And this can occur without any fine-tuning, without requiring any symmetry in 3D. But so if I have a crystal which has inversion and time reversal symmetries, every energy level is twofold degenerate. The reason is that what time reversal does is say, take psi k, if you like, k up. Let me give you an example, to psi minus k down. And what inversion does is take psi k down to psi minus k down. So time reversal flips the spin, inversion does nothing to the spin. Also, time reversal, of course, takes psi k down to minus psi k up. Right? So we have this sort of classic action of time reversal with the minus sign. So t squared is -1. So if I take the operation I times time reversal, you can convince yourself that this takes psi k up to psi k up, right? But it basically it enforces, being sloppy, it takes psi k up to psi k down, and so this should have been a minus k as well, psi k down to minus psi k up. So the product of time reversal and inversion is something that acts on a single point in k space. So normally when you think about time reversal and inversion on their own, they only they can only enforce degeneracies or do anything special at special points which are invariant under the operation. That's because time reversal generically sends k to minus k, but inversion pulls k minus k back to k. So if you have both those symmetries, you can look at the product and notice that the product of these symmetries acts at the same k point. It sends k to k. But also the product of those symmetries basically squares to the squares to -1 because of this operation. So you can apply it twice and your wave function picks up a minus sign. So basically what that tells you is that Kramer's theorem applies not just for the whole crystal, but applies effectively at every k point. So every energy level would be twofold degenerate if you had both time reversal and inversion. But if I break either time reversal or inversion, then I can have a single energy level at a point in k space, and that's very important. So if I have this kind of system, then generically, if a pair of bands touch, then the dispersion near the node can always be brought into the form some overall identity, which is just telling you the basic zero of the energy, kx sigma x, ky sigma y, plus kz sigma z. Because it has to be Hamiltonian is Hermitian, and it's these k, x, ky, and kz are measured about the points where the bands touch. Now, if I look at this is like the Weyl equation of particle physics, but the important thing to look at is that I've used all three Pauli matrices. Now, it means that if I do any small deformation to the problem, I cannot gap a single node. What does that mean? So let's just sketch what that looks like. So I've told you that I've taken this vial semimetal, and I've got some point over here, and I'm measuring kx, ky, and kz from that. So my h is mu times the identity plus kx sigma x plus ky sigma y plus kz sigma z. Right. So this is the dispersion. Let me add any perturbation. So let me say h goes to h plus delta h. Well, delta h has to be Hermitian, which means I can write this as a times the identity plus some b vector dot sigma, right? Any whatever parameters go into h, it has to be writable in this form. Any small deformation. What I mean by small deformation is that I'm not allowing you to do something like bring in another band and bring it here and so on. I'm only allowing you to work within the space of these bands that were already there. So I'm doing a small perturbation. I'm not doing something gross like bringing in additional bands from other energy. If I do that, then I have to expand my problem. I can't work in that 2x2 subspace. So this is what I mean by local stability. It means that I'm not bringing in any other states, and in particular, I'm not bringing in another while point from far away, because if I bring this in, then I have to do perturbation theory with multiple degenerate states. So for instance, if there was another while point and I brought it in, then I would have a 4x4 matrix, and I couldn't write the perturbation in this way. So I'm imagining that I can continue to do the perturbation in the subspace of the two states that cross. So there's some strength of perturbation statement there, right? So for instance, if there was a band that was far away and I had if this delta H was of this size, this is not allowed. Delta H kind of has to be somehow local to that point, and I'm really not doing things that can link me to bands that are far away. Within those rules, you see that H plus delta H just looks like mu plus A plus Kx, let me write it as K plus B dot sigma. And so all I've done is take this Dirac point and either A moves it up in energy and B moves it around in momentum. So the point is still there, it's just moved away from where it was before, but there's still this band crossing that's there. That's what we mean by these points being locally stable, right? So they're locally stable, and so we can build they're robust features of the band structure. I didn't need to tune anything to get this. As soon as the bands cross, I don't need to make some assumptions of any other, if for instance, in 2D, I have to give you a reason why I can't put on a constant times sigma z term, which would then gap out the node. But in 3D, because I have enough momenta to occupy kx, ky, and enough momenta to use the x, y, and z Pauli matrices, the 2x2 level crossing is protected and stable. It can't be moved by local perturbations. Yeah, is that argument clear? So this is what I just gave you in that sketch. An isolated node in the Brillouin zone is robust. Of course, this assumes translational symmetry because I was using momenta to label my states. If there's no translational symmetry, then in principle, I can just scatter to another state. I'm not allowed to use momentum as a good quantum number anymore, so I have to be a bit more careful when I do that. The second fact is that there's a certain sense in which the Pauli vector winds around the node. So if you look over here, sigma dot k and minus sigma dot k have slightly different behaviors, because in one of them, if you like, the way I think about the Pauli wave vector, it's aligned parallel to this node as I go out. In this one, it would be minus sigma dot k, so the Pauli wave vector is aligned anti-parallel to the node. And that defines a kind of handedness to these nodes, which is the chirality. Why that handedness is important is because based on the chirality, if the chirality is positive or negative, so what I've got is some k dot sigma dispersion, right? So think of that k as something like an effective magnetic field. Now imagine I take this node over here, this while node over here, and I draw a sphere around it in momentum space. So I'm going to ask you to imagine that because my artistic skills are not great. So I imagine shading a sphere that wraps around that node. That's a 2D surface in momentum space. And along that 2D surface, my effective Hamiltonian H effective is like sigma dot k. So let's say that that k is fixed. That's like saying there's a net flux out of this sphere in this picture. So if you now do, and it's saying something about, and remember that there's this node, away from the node, some states are occupied and some states are empty, right? So if I look away from the node, there's some set of occupied and empty states. And so on that surface, I can ask, how does the Berry phase evolve? And I can ask about the Berry flux through that surface. Because it's a two-dimensional surface, I can ask about the Berry flux through that surface. And what you can show by a careful calculation is that that's like a monopole of Berry curvature. So remember, the Berry curvature integrated across any 2D surface has a quantized value. And if I integrate a closed 2D surface, if I integrate around this closed 2D surface, it has a quantized value of 1. But if I go across this other node, I integrate across this closed 2D surface, if I do integral b dot dk on this surface, this is equal to -1. And over 2 pi or whatever. And if I do integral b d2k, this is equal to +1. So these are monopole sources and sinks of Berry curvature. And that's the key to understanding the non-trivial properties of these Weil semimetals. One important fact is, if you think about having a monopole flux source of Berry curvature, imagine I just had a single point over here that was a monopole of Berry curvature. Because the Brillouin zone is a torus, you run into a problem, because when I get to the boundary, I have to continue in over here, and I have an ambiguity, because if I approach it from the interior, I get that the Berry curvature should point out. If I approach it from this side, it looks like it should point in. That tells you that there's a contradiction to have a single monopole flux. You can't have a single monopole of anything inside a periodic system. You have to come in pairs, because otherwise your lines of force cannot close up on top of themselves. So a way to think about how these things can appear is if you start with a band insulator of this kind. So what I'm imagining here is that each of these energy levels are twofold degenerate. So what I've done here is imagine a band insulator which has inversion and time reversal symmetry. What I'm doing is bringing it to a point where now, if I look at this point, there's actually a 4x4 matrix at this point, which I can think of as two copies of these Dirac points. So these Weil points, that's why I've drawn it in purple. If I now break time reversal symmetry, I can peel these apart into a pair of Weil nodes. And then effectively what I've done is I can think of the Berry flux as now assigned to flow from one to the other. Of course, this is ambiguous because the Berry flux could flow in any trajectory it wants. There's no gauge invariant way to define that flux between those 2 points. But the key point is if I draw a surface around this and a surface around this, they have opposite Berry fluxes. So if I draw a surface around both of them, there's no Berry flux that has to leave that surface because there's a monopole and anti-monopole inside that. So the overall Brillouin zone is happy. So this is a picture of where a Weil semimetal appears from, starting from a band insulator, going to a Dirac point. A Dirac point is 2 of these Weil points on top of each other, and then splitting once I've broken time reversal symmetry, I allow it to split like that, right? But this actually tells us something interesting. So for instance, if I imagine taking a problem, let's look at this Brillouin zone again that I got in the Weil semimetal. Now, let me imagine taking a slice through this surface. Now, I can think of a particular example of a Weil semimetal where the slice through this surface, if you like, is something that doesn't necessarily, I can think of the slice through this surface as not necessarily separating the 2 things. So I could have just drawn the same picture with the kind of this arrow pointing the other way, and that's a material specific detail on exactly where the Berry curvature is, right? I've taken a simplified example, but what you can argue is if a slice through this surface has no Berry flux, then a slice through this surface has to have a Berry flux. And that's because the Berry flux that comes out of this has to go somewhere. By drawing this surface, I've told you that the Berry flux cannot possibly pass through this one. It cancels whatever comes out of that node. So it means that it has to be that there's a net flow of flux from here to here, because I know that if I draw a thing that encloses only this one, there has to be a flux going out. So by kind of drawing pictures like that, I can argue that somewhere in the Brillouin zone, there needs to be a slice that has a non-trivial Chern number. Now, if a slice of momentum space like this has a non-trivial Chern number, that's a 2D. I can think of that as effectively defining a 2D system at that fixed value of, in this language, fixed value of ky. So if I look at that fixed value of ky, I have an effective 2D system in the xz plane at that fixed value of ky. Now, if I say, let's look at a surface in the z direction. So what I've done is I still have kx and ky as good quantum numbers, but I'm thinking about a slab of the system that's finite in the z direction. It's a finite slab. Then on the top surface, every time I have a non-trivial value of this this integral of the Berry curvature, a non-trivial Chern number, I must have a surface state on that z surface. And so that surface state will exist for every value of ky on that, every value of kx and ky on that surface, such that there's a non-trivial Berry curvature associated with that. So you can convince yourself by drawing these pictures that there must be a band of such surface states, but these are just edge states of a 2D Chern insulator. So they disperse in the direction, in this case, in the x direction, because I fixed ky and kz and kx were good quantum numbers in that problem. I computed a Chern number. Now I relaxed the fact that kz was a good quantum number because I took a finite slab in the z direction. So you can do a trade-off. You can either have a non-trivial Chern number and have periodic boundary conditions, or you can have an edge state and open boundary conditions. But that edge state is chiral because of the nature of a Chern insulator, which means that On this surface, the edge state disperses that way, whereas on this surface, it disperses that way. So if I translate that, it tells me that there must be a line of dispersing surface modes that gives me what is known as a Fermi arc. So I have a surface state whose energy momentum relation tells me that it sort of disperses only that way on this surface, and on the bottom surface, it disperses in the opposite direction. So for each kx, I have a chiral flow of electrons going in that direction on the top surface, and a chiral mode of electrons on the bottom surface. So there's a whole stack of chiral modes in this problem. The top and the bottom of this problem together give me something that looks like a legal Fermi surface. But just looking at the top, it seems like I have a line of Fermi points that doesn't, a normal rule is that if you have a line of Fermi points, they separate occupied and empty states. That isn't true on the top surface because there isn't such a picture of what's going on. And that's because of the fact that this thing cannot exist on its own. It has to exist with this non-trivial bulk. Okay, so that's the basic picture of where you get these Fermi arc surface states from. So as somebody pointed out earlier, you can at least see the existence of these kinds of states with photoemission. So there's a sort of set of beautiful experiments originally on the material tantalum arsenide, which is supposed to be a Weil semimetal with a ton of Weil nodes. And the key picture on these experiments is you notice that there are these states that look something like this. So it turns out that these materials, for various reasons, have two sets of Fermi arcs that come out. So there's, both of these are Fermi arcs, but the way you see that they're Fermi arcs is to imagine increasing the energy as you go. So as you go down this curve, you're increasing the energy. And if you look at the comparison between this and this, if you take an ordinary Fermi surface and increase the energy, a closed Fermi surface, you would start with something like this and maybe go to something like this. Whereas in a Fermi arc, as you increase the energy, you would start with something like this and then grow bigger like that. So you have a sense of how the energy momentum relation behaves. And so in the picture that they have, even though this looks closed off, this crescent goes to a bigger crescent like that. And so it tells you that this state and the states on the two sides have the same energy momentum relation. They both are chiral moving to the right. Whereas in an ordinary Fermi surface, as you increase the energy, this state has to go outward, it has to grow that way, and this state has to go that way. That's the sensible ordinary Fermi surface. So the fact that both of these evolves to something bigger like that tells you that it measures the chirality, tells you the energy momentum relation has a handedness. It's moving in one direction on the top surface. So that's the evidence that these things are Fermi arcs in photoemission. So tomorrow I'll discuss other signatures of these Fermi arcs, which are more, as somebody pointed out, the fact that they're conducting isn't evident in ARPES, that the surface states exist is there. And this gives you some indication, although it's not perfect, gives you some sense of how they disperse chirally. But there's other signatures about these that I'll talk about, particularly in a magnetic field, that really pin them out as Fermi arcs. But what I want to do is say a little bit about candidate materials. So the original candidate material for these things was proposed was the pyrochlor iridate materials, and where A2IR207, where these A's originally were proposed to be Y or Europe or EU. And the reason for these materials is that they look at these materials is, to get these Weil semimetal-like physics, you want to have a combination of time reversal breaking. So magnetic materials are good, but you also want strong spin orbit coupling because you want there somehow the conduction electrons to care about the time reversal breaking in a particular way and feedback. You want the magnetism to feed back on the band structure. So this focusing on iridium is good because it has a very large atomic number and therefore has strong spin orbit coupling. And also the bands are relatively light in many of these cases, relatively flat, so there's singular effects. So if you vary this material A, that's like changing chemical pressure. It varies the interaction, sort of a Hubbard U between the iridium 5d orbitals. So what was understood is that as a function of U, you have an all-in, all-out magnetic order. As a function of U and an external field, you can look at a phase diagram in this way. And so at zero external field, you have this all-in, all-out magnetic order that exists, which says, which I've tried to draw over here, these pyrochlor is a lattice of corner sharing tetrahedra. And so all in, all out order means that there's a natural sense in which some tetrahedra point up and some tetrahedra point down. All in, all out means that the magnetic moments point into up tetrahedra and out of down tetrahedra or something like that, roughly speaking. And if you do LDA plus U on this material, what you find is that there's a region in which there's a Weil semimetallic phase with 24 Weil nodes in the Brillouin zone. So there's Weil nodes are at some weird points there on high symmetry surfaces, but split off from the center of those points. There's sort of 24 different Weil nodes in this material. And there's a whole bunch of other interesting states that can form, but the key thing to take away is that there's a robust regime where this material is believed to have a Weil semimetal phase. There have been experiments subsequently, and it still remains not 100% clear what the status of the iridates are, although more recently it seems to be that there are certain iridates with some level of doping that can get you into a Weil phase. But there's also simpler toy. You can engineer these Weil semimetals and heterostructures, really engineer them along the picture that I drew of bringing two Dirac points together and then splitting them with time reversal breaking. It's a very nice paper by Anton Burkov and Leon Belenz that pointed out if you take a heterostructure made of a topological insulator region, normal insulator region, topological insulator region, normal insulator region, and imagine that I can tune the separation, the thickness of either the normal or the topological region. Effectively, by tuning the thicknesses, what you can do is tune whether the dominant, so if I have an interface between a topological insulator and a normal insulator, I'll have a Dirac cone on each of these surfaces. And so what you can ask is if the imagine I take this picture and shrink the normal insulator to nothing. I make the tunneling within the normal insulator very, very strong. So I just shrink this to nothing. If this delta D, which is the strength of coupling between the two TIs, adjacent layers of TI, is very strong, then what happens is I gap out, the normal region is absent. So basically what I do is the Dirac point, so let me draw Dirac points. The Dirac point of this TI gaps out against this TI, Dirac point of this TI gaps out against this TI, of this TI against that, leaving an unpaired Dirac point on the top and the bottom surface, because that doesn't have anybody to gap against. In contrast, if I make the same layer coupling very strong, then the Dirac point of, change color. The Dirac point of a TI layer gaps out against its own Dirac point, so there's no leftover surface state. So you can see that by tuning the ratio of delta S over delta D in this simple toy model, I can go directly from a TI to a trivial insulator. So this should have been trivial insulator. So this line is essentially a phase transition between a TI and a trivial insulator. And it turns out that it's known that that phase transition is precisely a case where you have a single Dirac point. If you now incorporate magnetism, that's what these magnetic moments are, then for a sufficiently, basically when the magnetism comes in, what it does is it splits up this transition into a pair of transitions. And there's a large region where you have a Weil semimetal. So roughly speaking, what's happening is you have this Dirac point. So you have your 3D Brillouin zone. You create a Dirac point over here, which has two of these Weil. So let me say there's a plus and a minus Weil point right on top of each other. And then you pull them apart until at some point, if your magnetism is strong enough, you pull them apart all the way and you've annihilated them, you bring them back on the other side, and once the Dirac points on top of each other, you can gap them out again. In that limit, what you've gotten is actually a quantum anomalous Hall insulator. It's like a stacked 3D topological, it's like stacking quantized anomalous Hall states one on top of each other in 3D. And that's essentially a sort of layered, that's sort of reflecting the fact that it's a layered material in that setting. But there's a large regime where instead you don't take it all the way across, you sort of end up partway. So drawing these pictures again, you end up with Weil points that are plus and minus Weil points that have not gone all the way across the Brillouin zone. So that represents along this line, depending on specifically, the strength of the coupling relative to some fixed value of the magnetization, you see that if you move along this line, you get a Weil semimetal, and there's sort of a large wedge of Weil semimetal here. So there's a point of principle that you can just engineer this in a material. Of course, to do this requires a lot of detailed chemistry, and it may not be possible to do, but at least as a point of principle, you have a controlled model that you can realize this Weil semimetal situation in. Now, in fact, there's another example that you can get, which I'll talk about as well, because there are also a lot of material examples of these, which are topological Dirac semimetals. So the picture I drew over here was a Dirac semimetal with both its which had a single point in momentum space where there's a fourfold degeneracy, where two Weil points sit on top of each other. Now, it turns out you can have a different type of Dirac semimetal where you have, let me try and draw this again just to make it a bit more interactive. So you can have the following situation. So you have your 3D Brillouins run. Imagine that I have one Weil semimetal with its plus and minus nodes that way, and another Weil semimetal with a minus and a plus node. I've drawn these exaggerated. You should think of these as sitting at this, these things as sitting at the same point. So really these two things are at the same point in momentum space. I've just split them up, drawn them separated from each other. So naively, if I give you a plus and a minus Weil point, you can generically, you need a symmetry to enforce that. So for instance, here, the reason I was able to have a single Dirac point is I'm staying at a critical point. It's not stable to perturbations. If I make delta D a little bit bigger than delta S, I go into the trivial insulator. If I make it a little bit smaller, I go into the, make delta D bigger, I go into the trivial insulator. If I make delta D smaller, I go into the topological phase and vice versa. But if I look at this picture, I say, I've got these 2 points. It looks as though I can gap these out. But the reason I put them in different colors is, suppose that one of these pair of Weil points transformed under a different crystal symmetry eigenvalue than the other pair. Then, while this is quite delicate, if I break a crystal symmetry, I can gap these out. As long as I preserve the crystal symmetry, I could prevent these from gapping out. It's like saying I have 2 Weil points, but I'm not allowed this perturbation that takes me away from the point where they're massless unless I break a symmetry. And it turns out that this is actually quite easy to get in lots of materials. So this was pointed out that Na3Bi, sodium bismuth or cadmium arsenide, especially cadmium arsenide is a well-known semiconducting material. Many people have studied it. These are high mobility systems, and these can be engineered into this setting. What makes these very attractive is when you do these things in the pyrochloroiridates or other cases, you get a lot of Weil nodes, so they're quite hard to study, or like the tantalum arsenide example. The nice thing about these examples is there's only 4 Weil points, and in fact, because they're forced to appear at the same points in momentum space in this Dirac semimetal, there's actually 2 Dirac points separated in the Brillouin zones. They're sort of very pristine in some sense, and you can make, they're good places to make contact with theory if you're willing to pay the price that you need to worry about a crystal symmetry protection as well. And in fact, you can do ARPES experiments, and the bulk of these materials very shortly after these predictions reveal that there's actually a bulk Dirac point in both sodium bismuth and cadmium arsenide. And what I'll tell you about tomorrow is that there's actually a whole rich set of quantum oscillation data, particularly in cadmium arsenide, that strongly indicates the presence of quantum oscillations associated with the Fermi arc. So that addresses the question that was raised earlier about whether, I think by Satyabrata, which was whether there are signatures that indicate that there's coherent transport on these Fermi arcs. I would say the first serious significant evidence of quantum transport in the Fermi arcs was a beautiful set of experiments by the Berkeley group led by James Analytis that actually crisply identified a set of contributions to the quantum oscillations that come from these Fermi arcs in Dirac semimetals. So that's what I'll say a little bit more about these, but maybe I should point out that what I want to summarize what I've said about Weil and Dirac systems. I'll say much more about them tomorrow because I'm going to talk about the robust topological signatures of these Weil and Dirac semimetals. And as I pointed out, they result from accidental degeneracies. They're not symmetries required. They're not degeneracies that are required by symmetry, but once they occur, they're protected. In a Dirac semimetal, again, the fact that the 2 Weil nodes occur at the same point, the fact that there was a crossing is accidental, but once the crossing is there, it's protected because of the fact that these things come in crystal symmetry partners. So whatever's happening in one crystal symmetry sector is reflected in the opposite way in the other crystal symmetry sector. But nobody tells you that a material has to have these crossings a priori in this system. So what I want to spend some time on before the next section I'll talk about is cases where symmetries can require a system to be semi-metallic and forbid it from being insulating. And that's what's known as a filling enforced semimetal. But before I go into that, I should pause again for another 5 minutes and pause and take questions because it's going to change gears a bit and step back to interacting systems at this stage. So maybe I'll ask if there are questions at this point. Niladri, are there any questions in the chat? Because I can't.
I don't see any questions here. So if you have any, if anyone has any questions, either you can raise hand or put it in the chat.
Because I'm going to stop talking about vial semimetals for today. I'll come back to it tomorrow. So it's probably good. If you have questions on vials, it's probably good to get those out of the way. And I'm going to change gears a little bit and sort of say a little bit about interacting systems now. Hence the pause here.
Mm-hmm. Yeah, I think the point that Satyabrata has raised is quite interesting, and we keep getting that in when you submit a paper, and it's that RPS signatures and transport. So
right.
That
so I'll
be good.
Great.
Yeah.
I'll definitely talk quite a bit about that tomorrow then.
Yeah. I mean, that would be useful because often, I mean, there is a bias. Oh, okay. There is a question coming. Yeah, I think you would be able to unmute.
Yeah, I think you can unmute yourself.
Yeah, I think this is this CD3AS2 and BISB. All these are in literature. They say it's Dirac semimetal.
Yeah. And
when you apply an external field, then you can kind of have two vial nodes and they become vial semimetal.
Right.
So in principle, is it true that the CD3AS2 from the band structure, from the E versus K phase diagram point of view, and bismuth antimony, the alloy, at there is a transition from a Dirac semimetal topological insulator to trivial insulator at 0.04 with antimony doping.
Right.
Now, all these are actually Dirac semimetals. You have just single point, and then you apply an external field, then you can have them converted to vial semimetal. But niobium phosphide and tantalum arsenide, these are termed these are actually vial semimetal. I mean, I really don't understand the difference between tantalum arsenide's EK phase diagram, which is not a Dirac semimetal, it's a vial semimetal only, whereas technically CD3AS2 is a Dirac semimetal, and you have to put an external field to break the symmetry and make it a vial semimetal.
It's not that the external field is really it is breaking the time reversal symmetry and splitting apart the nodes, yes. Yeah. I mean, I think you can't see it. The E versus K band structure has that information. It's just the way it's drawn. My personal view is every E versus K band structure should carry little labels of multiply by 2 every time there's a twofold degeneracy. So if you look at the E versus K bands of, say, cadmium arsenide, if you look near the nodes, what actually happens is there's a 4-fold degeneracy. You can actually check if you're doing it carefully and you look at the K.P theory, which is done in these original papers. I don't think I have a picture of that. But if you look at this paper by Zijun Wang and others, what you see is actually there's, if you wrote down the minimal model for that crossing that happens over here, it's actually a 4x4 matrix Hamiltonian. But if you take tantalum arsenide and zoom into any of those points that you cross, you only need a 2x2 matrix because spin orbit has been fully incorporated into that. I'm not saying they're not spin orbit coupled, but if you look at the actual band structure, you need a minimum of a 4x4 matrix to do the K.P theory for cadmium arsenide at any of the two nodal points. Whereas in tantalum arsenide, if I look at the individualized band structure, what you'll find, if I look near any of the points, it'll only be two levels. I can do a 2x2 K.P theory, even including spin. And that's a sharp distinction.
Yes. And just another small question. These quantum oscillation measurements.
Yes.
I mean, it is not, I mean, even if you have a good crystal of copper, one can see this Subnikov-Dihas oscillation. So it is a surface. To say that it is coming from topological characteristics of surface, some more clarity is needed. Maybe probably tomorrow you show the signatures. But the problem is the ABJ is also considered the true test of longitudinal magnetization, negative magnetization, and all these things. I mean, tomorrow we do expect that more clarity on these measurements. These can be very, very confusing because these can come from different reasons also. Even anomalous Hall effect.
I think you're asking the same question again. So I'll give you the same answer again, but I'll answer it tomorrow.
Yeah.
Right? I sort of clearly said what I was
the telltale sign of a vial semimetal.
Yeah.
which cannot be anything else but wild characteristics. Yes.
Great. No, that's a great question. I repeat that it's a good question. It's just that I can either give tomorrow's lecture to
tomorrow,
take
yes.
a day off or do it tomorrow. So whichever you prefer.
Thank you.
Yeah. Other questions?
I didn't see anything on the chat.
Okay.
Okay.
So yeah, I promise I'll answer those, at least try and give you a partial answer. I think it's, it's an area of research, so there's still sharp questions. I think we even have very recent results that suggest, at least in cases where for certain types of vile semimetals, there are additional effects that are very hard to explain without involving Fermi arcs. So we have some nice new results that are coming out that came out of thinking about very different questions about quantum oscillations in 2D systems. So I think there's a lot, it's still very much an active area to think about exactly what the sharp oscillations are. I would say that with quantum oscillations, there's particular signatures that have to do with size dependence and focused ion beam lithography on samples that really allows you to, it would be very hard to explain any of those experiments without referring to, it'd be very hard to explain any of the experiments without referring to somehow the work, without thinking about topological Fermi arcs. Similarly, I don't necessarily subscribe to, so we've made some predictions for chiral anomaly related magnetoresistance, and even there's ways to argue certain, I would argue that pure longitudinal magnetoresistance, I'll tell you tomorrow, can be very hard to tell apart and say it's topological. There are tricks that you can do which are multi-terminal measurements done in clever ways that are more disputative, that actually tell you that, okay, this is unlikely to be something that comes from some ordinary thing, because what we've done is try and separate out the contribution that is characteristic of vile nodes. So, but again, it's a very hard problem, and it's one of those things where experiments have to, we have to work hand in hand with experiments, and each example you need to work a bit clearer. What we're trying to do is find some generic tricks to tease out what's there, and I'll say I'll give you a short version of the answer is, ultimately, what you want to think about is look for signatures that are intrinsically non-local, that are really involve some interconversion of charge into some other degree of freedom, either things associated with Fermi arcs or things associated with bulk valley transport that can lead to long-range effects in transport that you wouldn't believe can come out of ordinary ohmic bulk conductivity. And those things at least give you stronger evidence than pure longitudinal magnetoresistance. So that's a preview of the answer tomorrow. Since the question was asked so many times today, I felt I should give an answer today. Okay. Okay. What I'm do is just spend the last 15 minutes or so saying a little bit about how gaplessness can be forced upon you by topology. And this will just give you an example of how these sort of Laughlin-like arguments can play a useful role in clarifying semimetals, and it'll also kind of place different semimetals in context. So I'm going to remind you of a very different aspect, which is of condensed matter physics, which is Luttinger's theorem. And Luttinger's theorem is basically, you can phrase it in very complicated ways using diagrams, but the basic picture is the volume of the Fermi surface is protected even if you have interactions. So what that says is, if I give you an initial density of electrons in your system like this over here, well, interactions could change my dispersion by some correlate, by changing self-energies and stuff. So you could change the shape of the Fermi surface. You could even do something drastic like, upend the Fermi surface and say, oh, well, I'll push it all over here, or create, electron and hole pockets by deforming the band structure. But no matter what you do, if interactions don't open a gap, all these things can be thought of as changing the shape of the Fermi surface, but not its volume. And I'll remind you that having equal volume electron and hole pockets is like adding 0. So this exactly cancels this. So if you actually go back and ask, how can I open a gap in something like this? Well, you could break a symmetry. For instance, you could break U1 symmetry and get a superfluid, or if you're a commensurate filling, you could get antiferromagnetic order or something like that. Or in a much more exotic situation, people have discussed various topologically ordered ground states. And these ground states typically have some kind of non-trivial ground state degeneracy, and they involve fractionalization of quantum numbers, right? So in fact, Luttinger's theorem is sort of interesting. It was obtained by doing, diagrammatic perturbation theory and so on. But in fact, there's a modern view of that, mostly due to Oshikawa and followed up by various people, that actually links it to Laughlin's argument. And in the modern language, this is viewed as an example of what's called a 't Hooft anomaly in particle physics. It's a fancy word. But basically what these things are Luttinger's theorem is really telling you something, that a piece of physics that's microscopic is influencing a piece of physics that's macroscopic in the infrared, in the long wavelength physics. So let me write Luttinger's theorem in a kind of suggestive way. Let me take a crystal that has translational symmetry, so I can define a unit cell, and that has some conserved charge, like electrical charge. Then there's a microscopic charge that I can associate with each unit cell, right? So there's a microscopic charge in each unit cell. And what Luttinger's theorem basically says is I can divide that up into two things. I can divide that up into a charge that's sitting in filled bands, because for instance, I could have, if I think about the microscopic charge in every unit cell of a crystal, it could be very, very large, because in principle, the microscopic charge includes, if I take some complicated atom like iridium, for instance, its atomic number is 77. So there's, huge number of filled bands due to inner core electrons, right? So that's in principle there in the microscopic degrees of freedom, but I tend not to worry about those because that gets stuck into filled bands. So most of the time, the Fermi surface we're talking about corresponds to the little bit of charge that's not accommodated into filled bands. And the long wavelength properties really care about this, and I ignore that. So if you like, what Luttinger's theorem tells you is that the protected Fermi volume is whatever fraction of charge is the fractional piece of the charge, because everything else can be dumped into filled bands. And actually, this can be given a very nice argument, completely independent of any diagrammatic theories, because what you can do is ask about how the ground state evolves under some Laughlin argument and ask how much momentum flows into the ground state. And that can be related to the volume of the Fermi surface, because every quasi-particle has some momentum. So if the momentum of the ground state shifts, then in a Fermi liquid, the whole if every quasi-particle changes its momentum, the whole Fermi volume moves, and so you can count the Fermi volume in terms of the microscopic momentum, and that's linked to the charge per unit cell. So Luttinger's theorem is really one of a class of microscopic constraints that your low energy theory has to satisfy. So it says, I don't care what you do with your Fermi liquid. I don't know anything about the details, but you better not change the Fermi volume, because that is somehow has to be there to respect the symmetries of the system, which are set microscopically. No matter what, if you break the symmetry, you're allowed to get away from it. But if you want to preserve those microscopic symmetries of translation and charge conservation, then there has to be some total Fermi volume that's protected. It can't be changed. You can do whatever you like, deform it, do anything else, but you must give me that much filled charge. So the basic idea is to do this is you insert something that's a gauge flux, and so you can do this mathematically. You compute how the ground state momentum changes, and you ask, how does the Fermi C accommodate that change? So what this does is say, if I have a low energy theory, where Fermi surface exists, and I have some microscopic data, which is the charge per unit cell, I do two calculations of the same quantity. How does the system respond to some change in boundary conditions or some gauge invariant process? And I ask that these two must agree. So one is done microscopically. It doesn't make any reference to what the state is. It just says there were this many charges per unit cell. The other one says, suppose the low energy theory is a Fermi liquid, what should it do? If it has a Fermi surface, how should it behave? Right? So the way this works is actually almost very, very simple. So imagine I have a system of charges, right? I don't say anything about this except say there's some number of charges and there's some unit cell. So what I'm doing is imagine I take my system and I put it on a torus, and through a hole of the torus, I thread a flux. So I have phi of t such that phi of 0 equals 0 and phi of t is 2 pi. So I ramp up the flux. Now, what is the force that I see? Well, what I want to do is look at the force is related to the EMF on the system. So you can convince yourself by just elementary electrodynamics that the force on the system is 1 over Lx d phi dt, right? Because this is just Lenz's law, except that I'm setting charge to 1. But what I want to do now is the total force. So this is force on each electron in my system. So F total is going to be sum over all the electrons d phi dt, or if you like, I don't really care, I can just say this is just the total number of charges times d phi dt, right? So this should be clear. So that tells me the way I get this delta p, and this is in the x direction. This is x, and that's just, you can see that from Lenz's law, this is the nature of the force that would act on the system. So my delta px, the way I get this is to write this as integral fx dt, and that's just going to be n over lx times 2 pi. Right? That's the way I get this calculation, because I just integrate this over all times, and I told you that the total flux that flowed through the system was 2 pi, so it's just phi of t minus phi of 0 is just 2 pi, one flux quantum. And now if I think of n is equal to the density, the filling times the number of unit cells, I obtain this result over here. Okay? Of course, in this picture, I just counted unit cells and I talked to you about a total change in momentum. But we know, though, in a crystal that a total momentum isn't a good quantum number in the crystal. Only crystal momentum is a good quantum number. And so if this filling nu happens to be, if nu is not an integer, then the total change in momentum is actually something that even in the crystal, I can tell the difference between the initial state and the final state. There's a non-zero change in the crystal momentum of the system. If this thing was an integer, you wouldn't be able to tell the difference of what was going on. You would have to say that you wouldn't know anything about whether any quantum number changed in this problem. You can do this much more formally, but basically this picture tells you that if I have a system where I have a filling that's not an integer, then in principle I can construct an experiment, in this setting, I can construct an experiment in which threading 2 pi flux changes the ground state of the system. Now, if I have a system where the ground state, the low energy description is a Fermi liquid, we know that it just says that there's some interactions between the electrons, but I can label things in terms of momenta. Now, when I insert a flux, you can convince yourself that what I do is under flux insertion is just remember that the flux insertion, a time-dependent flux is like an electric field, and under an electric field, it just acts on momentum. Remember the equation we wrote down, which is k dot is equal to E. So the k dot is equal to E. Under an electric field, over some time, I just have to ask how much does the momentum change. So every unit of time, the momentum changes by an amount d phi dt. So you can convince yourself that over the total insertion of the flux, before and after, every quasi-particle at momentum kx is now at momentum kx plus 2 pi over Lx. You can use Stokes' theorem to convert that into a statement that since every quasi-particle moves, but in the end, most quasi-particles move into a state that was emptied by another quasi-particle. The only place you see the change is near the boundary of the system, because that's where you emptied some states and occupied some states. So you took a Fermi surface that was like this and boosted it over. And if you do this calculation carefully with Stokes' theorem, what you see is that the change in momentum in a Fermi liquid is related to the Fermi volume multiplied by the same coefficient 2 pi Ly. Now you have to do some little bit of futzing around with number theory, because you have to do this for every system size Lx and Ly. You have to convince yourself, and this can be done. You find that this nu is related to the volume of the Fermi surface, but of course, the only thing I can get from this is the part that wasn't absorbed. So for now, I'm taking this filling to be the fractional part, because anything else I couldn't tell apart from 0. So that's the basic version of deriving a theory for Luttinger's theorem for a Fermi surface in this kind of abstract way. But I want to ask now, suppose I have a semimetal. I have equal volume electron and hole pockets. I can get this in 2 ways. I can take a band insulator like this and pull this band below the Fermi energy and pull that above the Fermi energy, so that I have equal volume electron and hole pockets. Another way I can get equal volume electron and hole pockets is to start with something that was like fundamentally a semimetal and pull the bands above and below the Fermi energy, so one Dirac point went down and one Dirac point went up from the Fermi energy. And there can be an example in which I can deform this all I like, but I can never get rid of the fact that at least there's a nodal point on the Fermi surface. So I want to ask, is this boundary real? Is there really something that tells me these two things are different? And in a limited set of cases, there is. So the problem with running the arguments earlier is if I have no Fermi volume in the system, then you can convince yourself that the only way to get that situation with no net Fermi volume is to have an integer number of charges. I'm again forgetting about spin for the moment, to have an integer number of charges per unit cell. And I know that the charge in a filled band can always be an integer. And so that means the charge enclosed by the Fermi surface must vanish. So it seems like I don't get anything protected, that 0 is 0. So what I want to argue is that this zero volume and this zero volume are different. That the zero volume in some kinds of semimetals is hiding something that tells you the bands have to stick together. And the way to think about that is in certain crystals, you cannot introduce individual bands to suck up electrons. You have to introduce bands in groups. And it turns out that these are crystals which have what are known as a non-symmorphic symmetry. A non-symmorphic symmetry is a symmetry where you have to combine a rotation or a reflection with translation by a fraction of a lattice vector in order to leave the system invariant. And it turns out that these kinds of systems are quite special. We started looking at them a while ago. It turns out they have a lot of very interesting properties. And so here's some examples of crystals. So one example is the Shastri-Sutherland lattice in 2D. So it's a crystal where there's some pattern over here, and you can see that this pattern has the property that if I do a reflection, it doesn't go back into itself. But if I do a reflection and a translation, this is a lattice vector. If I do a reflection and a translation by this bit, then the crystal goes back into itself. And there are other examples. For instance, if I take a HCP crystal and do a 60-degree rotation, I turn A sites into B sites. But if I do a 60-degree rotation followed by a translation by C/2, I return the crystal to itself. So it turns out, and I won't go into the details, if you follow this argument over here, you can actually show that there are non-trivial invariants associated even with the vanishing Fermi volume. And what that means is that there are crystals in which bands are forced to exchange. So in all these non-symmorphic crystals, the bands are forced to be glued together in pairs such that two bands are required. So even though you have, basically what you find is bands always appear in pairs that swap as you move across the Brillouin zone. And the fact that two bands swap means there has to be a non-trivial level crossing. And so this topological invariant measures the fact that as you send k to k plus 2 pi over L, you actually change the momentum of some quantum number of the system very slightly because you needed to you basically change something near this nodal point. And the interesting thing is that you can show that if the system were gapped, nothing would change under this transformation, or if you had filled bands. So it's sort of a very special feature for when the chemical potential is forced to cross these points. And it turns out, and I think I'm running out of time, but one interesting example is that if you like, in the original model for 3D TI was this beautiful example of Foucault and Millet. And what you can show is that that model has this special protected property until you introduce a distortion that breaks its crystal symmetries. And so that explains why the Foucault and Millet model has a Dirac point on its zone boundary. So this is a design principle for finding Dirac semimetals. And so just to wrap up, you can apply this to various things, but what these tell you is that there's sort of gapless phases suggested by both this Thouless approach, which I said these Weil semimetals, just thinking about band structures and Berry phases gives you this example, whereas you also get these filling enforced semimetals. And it turns out that this allows you to peel apart 3 different types of Dirac semimetals. So for instance, when the idea of Dirac semimetals came in, there was a lot of confusion because there were these Dirac semimetals like cadmium arsenide and sodium bismuth, where you had these nodes in the Brillouin zone interior that had these Fermi arcs that were quite interesting. Whereas there were other cases where there was only one pair of Dirac points. So, if you like, these are the Dirac semimetal in cadmium arsenide is like 2 copies of a Weil semimetal in 2 different crystal symmetry sectors. So if you like the way the Weil nodes are paired, a Weil node is coupled to a Weil node somewhere else in the zone. It's not really partnered with the Weil node that's present at the same point in momentum space. That's why they're non-trivial. There's a different type of Dirac semimetal that Charlie Kane and collaborators found, which has nodes in the Brillouin zone boundary, and it turns out that the Foucault and Millet model is of this example. So this does not have any Fermi arcs or anything like that, because if you like, the 2 Dirac points that are forced to appear next to each other are actually at the same point in momentum space. And it turns out that you can also get things that combine both these features that are both that have nodes in the interior of the Brillouin zone, but still have some non-symmorphic symmetry, so that kind of have the property that they're enforced by the filling, but also have some non-trivial surface states. So what I've spent today, I didn't want to spend too much time on this last bit, just pointing out that there's sort of abstract results that you can get that force you to have certain semi-metallic dispersions, just like having some odd number of electrons per unit cell forces you to be metallic. Similarly, certain crystals have a property that they are forced to be semi-metallic, and those are these ideas of filling and forced semi-metals, and many people have worked on them, including Ashwin's group since then. And so to close today, what I've talked to you about as a summary is just giving you an overview of topology in solids from the lens of Berry phases. Talked a little bit about vile semimetals that came from these accidental degeneracies in crystals, and given you just a hint of these Fermi arc surface states. And as I promised, I'll say much more tomorrow, giving you some examples of the experimental realizations, and also told you about a version of a Dirac semimetal, which were two copies of these vile semimetals protected by crystal symmetry. And the last bit, I sort of took a step back and talked about cases where just fixing the electron filling can force you to be in a semi-metallic dispersion rather than insulating dispersion, and said that this might be a way to look for new semi-metals. But the problem with these filling enforced ones is their topological features can be more subtle. They don't necessarily have Fermi arcs. And so I think the thing to take away from this is that semi-metals can be topological in different ways. What I'm going to do tomorrow is spend most of my time talking about transport and thermodynamic signatures of these vile and Dirac semimetals. So let me stop there and leave the last 5 minutes for questions on today's lecture.
Thank you, Sid. It's an excellent lecture. I'm sure that everyone learned a lot. Any questions?
I still see a raised hand. I don't know if that's from before. From Satya.
I think it's from before. From Satya Brother, or unless you have some questions. Okay, I'd like to ask a quick question. Would you be able to comment at some point, maybe until tomorrow, because these are bulk materials that we have been talking about, where you bring in these different elements. Would it be also possible to see these effects in for example, in thin film heterostructures or 2D structures, where you can individually sort of bring in and utilize things like the proximity effect?
Yes, so I think proximity effect is an interesting question. I haven't thought too much about that. I will say that to me, the most elegant example of the quantum oscillations from Fermi arcs is this work by James Analytis, where they did focused ion beam samples. And because the point was, it's actually very useful to do thin films of these materials. The reason it's useful to do thin films is a lot of things to do with Fermi arcs can be diagnosed by looking at thickness dependence of things. Basically, because anything that involves linking the two Fermi, so the key thing in quantum oscillations of the Fermi arcs is there's a weird semi-classical orbit that involves evolving of the Fermi arcs, shooting through the bulk, evolving on a Fermi arc, and shooting back through the bulk. So while you're transported to the bulk, you don't have a magnetic field, but you have to traverse a distance of order L. And you have to traverse that distance at a speed set by whatever the Fermi velocity of the chiral mode is. And so if your thickness grows, you spend a longer time in the orbit. And if you think in semi-classical quantization, the energy of the orbit is set by the time it takes, right? Because you do 1 over time to compute the energy by the uncertainty principle. That's how you quantize it. So you say the time of the orbit must be quantized. That gives you a quantization condition on the energy. So that's a very neat statement, because what that tells you is that there's a thickness dependent oscillation frequency, and maybe you can tease that out of the sample. And in fact, the really clever thing that they did with these focused ion beam samples was to take a triangular, they could fabricate a triangular sample, and they saw that oscillations went away on the triangular sample, but a rectangular sample would not have that effect. So they argued, I mean, again, you have to want to see it, so you could come up with other explanations, but what you could argue in that picture is the triangular sample has a geometric interference effect that's absent in the rectangular sample. But both of them have been, massaged sufficiently that it's not like one of them had more disorder or something like that. They should be intrinsically have the same surfaces. It's just that the geometry of the surfaces was different. So that was a nice kind of experimental thing. So doing thin film experiments is actually a very neat way to look at a lot of these things. Especially a lot of the things I'll tell you about really require you to make contact to one surface and do something to the other surface. The problem is very often the reason they have to do fib rather than something else is you can't cleave the samples nicely in the direction that you want to, because you want to have the direction in which the arcs appear, but the arcs appear in a direction that's usually on the surface that's perpendicular to some nice growth direction if you're doing heterostructures or something like that, or the cleavage direction tends to be orthogonal to the arc direction, which is why fib is a nice way to do it, because you don't care about the growth direction, you just shoot the damn thing and it kills something. But then of course you worry that that's doing a lot of violence to the sample. There's lots of ionic stuff. So you know, that's the big against the. It's sort of surprising that you see quantum oscillations in a fib thing.
Yeah.
It's very shocking, and might be that there's another explanation for that. I haven't seen a compelling alternative explanation, so I like to say that that sample is a nice experiment, but I'm open to the statement that maybe that's not really the case. So,
yeah, I mean, that's the first thing that comes to your mind is the ion-induced damage when you're doing fib. But I mean, there are ways to get rid of it. But yeah, I think in thin film, this is one interesting point is the dimensionality of the system. I mean, how that plays a role. And also, I mean, whenever you're going to thin films, I think the question of the interfaces also come in.
Right.
I think, yeah, so that will be quite interesting too.
Yeah.